What's that?
Is it just a possibility that the proton enters the
I can't hear you. Say a little louder.
Is it only under certain conditions the proton enters the excited state?
Yeah, it's just going to be a huge amount of energy. So a couple of examples I've given you so far is you're regularly getting gamma radiation from the sun, because you can look at the sun there and are examining the sun. Yep, there's a huge amount of energy kind of going along up there all the time. Or the next one that I gave you is actually specifically in beta decay. There is actually a huge amount of energy in that particular process, which causes that to occur as well. Now, by the way, when I say huge amounts of energy, you're going to see me talk about this when I get to chapter 30. These are huge relative to the objects in question. The actual, in truth, a nuclear reaction, I think I made the joke last year that, hey, if a nuclear reaction happens anywhere in this area, if protons, I think what I was talking about with electricity, if protons move out of the nucleus, let me know, I'm going to move my family. In truth, if one proton does kick out of a nucleus regularly, you wouldn't notice the amount of energy that comes off of it. It'll be huge relative to that atom, but it's only one atom. A nuclear reaction, which you'll again see when we get to chapter 30, a nuclear reaction that is dangerous is one that is running away. Okay? Yeah, we'll get that when we get to chapter 30. I don't need to talk about that for right now. All right, so. Is your nucleus running? Yes, that would be fantastic. So talking about some of this stuff, like the radioactivity is used all the time. As a matter of fact, smoke detectors. Smoke detectors 100% use radiation in order to understand, in order to work. Your smoke detector consists of an ionization chamber, fancy way of saying they're going to take the atoms and make them have some charge. Okay, a sensitive current detector and an alarm. A weak radioactive source ionizes the air. So you put some radioactive source, some element in there that's going to go out and naturally strip off electrons and protons off of everything in the air, which are charged particles. Voltage is maintained between the plates inside the chamber, setting up a small but detectable current in the external current. That's essentially so. Your smoke detector always has a very tiny current going through it. As long as current is maintained, the alarm is deactivated. But if smoke drifts in the chamber, okay, the ions become attracted to the smoke particles. These heavier particles don't drift nearly as easily, and what happens to your current? Decreases sharply, and your alarm goes, hey, I'm annoyed, I don't have, but you'll also notice, of course, the benefit of doing it that particular way is you're also going to get an alarm when your battery starts to fail, because as your battery starts to fail, once again, for other reasons, the current is going to decrease, and if the current decrease is too small in that particular case, then your alarm goes off telling you, hey, something's wrong. In that particular case, it's just that the battery is gone dead in that particular spot. Okay, this is also used in radon detection, similar thing. If you ever have, downstairs basement, you absolutely have to have radon detection down there. Radon, of course, was the whole canary in the mine type situation. First radon detectors were send a canary into the mine and see if it's dead or not, and or it comes back. That type of deal. Similar conversation right there. Radioactivity is also used in radioactive dating. Specifically, the element that is used. Let's see if they have it on here. They not gonna put it up there? Let's go here. I thought that they had that on this one. Yeah, okay. So I told you that the most common carbon isotope is carbon what? 12. I said it's like 99% of all the carbon that there is. Okay? And then about 1% of it is carbon 13. Carbon 14 is inherently naturally radioactive. Specifically, we have found that it regularly goes through beta decay. Cosmic rays, which are high energy particles from outer space that exist because of background radiation that was there at the beginning of the universe, in the upper atmosphere cause nuclear reactions that create carbon-14 all the time. Okay, from nitrogen-14. So there's your beta decay the opposite way. But in the ratio of carbon-14 to carbon-12, these carbon dioxide molecules in our atmosphere maintain a very consistent ratio. Meaning, carbon dioxide can be made out of carbon-14, carbon-12, or carbon-13. There is an extraordinarily specific ratio between how much carbon-12 there is and how much carbon-14 there is. So, things like plants that breathe in that carbon dioxide are breathing in a very specific ratio of this right here. And as they develop all the sugars that we then eat, we, in our bodies, made of carbon, specifically that originally came from the photosynthesis of trees and plants, have a very specific amount of carbon-14 in us. And since we are regularly consuming that, that ratio should then be maintained. And for plants and animals, that ratio should be maintained because they're alive. But what happens when they die? Do they maintain the carbon-14 in their system after plants and animals and plants die?
Yeah.
No. They're not breathing anymore. Why should they take in more carbon-14 from the atmosphere? So now the carbon-14 in their body is set.
Yes.
Since it is radioactive, what's going to slowly happen to the amount of carbon-14 in their body? It's going to decrease. If we can then take a sample, we can measure how much carbon-14 should be there versus how much carbon-14 is there, right?
Yes.
That being said, using the half-life of carbon-14, we can then reverse engineer, using those ratios, how old the object is. Okay, that's the general principle of carbon dating and why it specifically works. Oh, by the way, it works for us too, because like I said, why do we have that ratio in us? Because we regularly consume all of that carbon from the sugars, so we should have the exact same ratio. And what do we no longer do when we're dead? We don't consume these things anymore. So once again, you'd have a set amount of carbon-14 in your body at that time, and it would regularly start to go away as you continue. So again, you can look at humans, anything at all, specifically that is made of carbon. So this means organic materials. By the way, hopefully we understand this. Organic simply means it's made of carbon. Okay, which essentially comes down to living things, because everything is built for the most part, 98% of the time, built out of these sugars, blah, blah, blah. We get the sugars, move on, so we have carbon-14. Okay, I'm going to give you a counter argument to this. And I don't give this counter argument to try to suggest that you should believe the counter argument. I just want you to understand the opposite argument to it. Okay, the teacher before me was, you probably know, I'm Christian by nature. He was extraordinarily Christian right on this, and he and I kind of butted heads on a few things, and this is definitely sort of one of them. But I do want you to understand kind of where certain lines of logic come from to be able to make your own opinions on this thing. There is a big assumption that is in this, that carbon dating is fundamentally founded on, and it's this. The thing that starts the carbon-14 process at the very beginning is this cosmic radiation. Okay? The amount of carbon-14 being created would then be fundamental, that the entire time this thing has been alive, or sorry, in this case dead, that should be carbon, that the radiation has stayed exactly the same. If the radiation was smaller back in time, would there be as much carbon-14? And if there wasn't actually as much carbon-14, then we today, assuming that radiation has stayed exactly the same, would assume that the thing is vastly older than it actually is. Does that make sense? This is one of the arguments that like creationists would say or I shouldn't say even creationists, young Earth creationists or Christians use to talk about carbon dating in this particular process. Now, I will say this, okay? I was a little bit weary in talking about this stuff because people can automatically take groups of people and say they're ridiculous, but this group of people isn't. Their line of logic on this, I would argue, is very reasonable, okay? Carbon dating has been seen to be a little bit ridiculous in certain circumstances. So stuff like that, I always try to be like, take with a grain of salt once you understand one way or the other. I'm not going to tell you how to believe either way, but I want you to understand where the idea comes from, and of course, potentially problems with it specifically. I have heard of kind of instances, case studies, where people have been like, hey, this is my, they'll send in like their cat that has actually been like fossilized after being in the ground. It got dug up, whatever, to a company like, hey, this is like an ancient cat that is like such and such so many years old. Like, No, it died a year ago. So carbon dating is certainly not perfect by any stretch of the imagination. But, all right, moving on. Let's talk natural radioactivity. Uranium, actinium, thorium, and newtonium. Do you remember what I said kind of is the stable? Lead, yeah, 82 up there. So what you're going to find a lot of them today is actually over here on the right side. Notice that every single one of these guys is pretty much ending over here at some stable isotope of lead. So uranium, actinium, thorium, neptunium, all of these will have half-lives over time. Now, half-lives meaning the uranium original sample isn't automatically there. So what happens to them? This is a good depiction of each of these steps that you're looking at right here is either alpha decay or it's beta decay. It's gamma decay is also in here, but you don't see it directly because a gamma decay is not going to change the actual element. So which one is this one and why? Thorium 232 to radium 228. That's alpha decay because it dropped by 4. Radium to 228 to actinium 228 to thorium 228. Those are 2 steps of beta decay, correct? Jumping from thorium down to radium again, but instead of 228, 224. So now we have another alpha, jumping 4, jumping 4, jumping 4. All 3 of those are, of course, alpha. These blue step right down here, of course, would be beta. And then you'll notice at this particular time, you can actually do one of 2 things to get to your final lead. You can either go alpha and then beta, or you can do beta and then alpha, but both are going to end result at the exact same lead. What you're going to see on your homework is stuff like, I would say something to you like, thorium 232 goes through alpha and then a beta and then an alpha. Show me with equations exactly where it should end up and what its final products would be. Yes.
What determines if it goes through alpha or beta?
What determines would be its original state and also a random chance. And what we're looking at right up here is probably more experimental data than it is kind of we understand exactly what it is that's going on. For the most part, alpha really comes down to, once again, the discrepancy between how many neutrons there are and how many protons there are. As we talked about, when there's too many neutrons, there's too big of a pull. Pulls will kind of start to rip certain pieces apart in that particular process. It's really just overall, when it comes to alpha, alpha is that push and pull between strong and electromagnetism. Alpha is the electromagnetism is pushing out, strong force is pushing in, and if it wiggles too much, it snaps off, and it snaps off in the form of alpha. Beta comes from that kind of weird weak force conversation, and gamma comes out of, like we talked about before, kind of the understanding of the proton jumping energy levels in that particular case. So gamma is always, does it have too much energy? Alpha comes out of, like I said, tug of war, and beta comes out of the weird one. All right, so nuclear reactions in this particular case, here we have helium plus nitrogen eating X plus some helium. And in this particular case, you're getting oxygen plus hydrogen. So notice there's a decided discrepancy between these equations and what we have been discussing, okay? The object starting big and going small, you probably know this already, is described by what word? Fission. Things are separating. They're fission. They're separating out. When 2 smaller things come together to make a bigger thing, we get fusion. They're fusing together. Yes. Okay. Which one is more practical currently for us? Yes, you're correct. Fission. Why? Because we have a huge source of objects that are naturally radioactive. Is the ultimate answer. We can do fission easier than we can do fusion. We'll talk about fusion here in just a second. But ultimately, these equations, as always, you go, hey, I've got 18 over here. I've got 9 right here. I'm putting out a hydrogen. That's 1, so that guy better be an 8. This guy's 18 up here. I'm putting out a 1, so this should be 17, oxygen 8. Come on, there it is. Or oxygen 17. Simple balancing the equations on that particular guy. So, that being said, which of the following are possible reactions? chose such like crappy numbers. But.
This makes it hard to do.
I mean,
Okay.
neutron. Lowercase b, lowercase n, and lowercase e are all neutron, proton, electron respectively.
So how did neutron become that? I like A and B.
We'll get to that. Let's just talk about it as possible.
I don't like C.
A is possible. I believe A is possible, yes.
I think it is possible.
I think B is possible.
I'll give B an S. No, I won't.
232.
Yes, I will.
Yeah, C. But C, I don't like C.
No, I don't like B.
You don't like B?
B should be fine. 236.
236 on top. I mean, 92's
Yeah,
fine on the bottom. So this would be what? 232. No, 233 plus 3 gets you 236.
I like B.
Good. I'm glad you came around. And then 240 on the bottom on the left side, and what is that? That's going to be 372, 220, 223. So yeah, so C shouldn't work. There you
C is gross.
go. Gross. Very.
Settling at 94.
All right, let's talk Q values real quick. I thought I was going to end early. I'm not, but Q values I'm pretty sure is the end.
Oh, it's the unstable.
Yeah, I'm not going to talk about radiation damage, so we're good. So a Q value actually puts math to what it is that we were discussing. So when you find masses of normal elements, okay, the average element, you can use the periodic table because the periodic table is an average. But if you are looking at an individual reaction, you cannot use that table right up there because obviously isotopes are going to be of various sizes. So all these isotopes had to be measured individually. So when you ask the question, where do some of these masses come from in just a second, by the way, I realized that I was talking about fission and fusion. I forgot that's in the next chapter. So that is true. That is where these come from. This last whole set was not trying to be, are they possible? It's just kind of making sure you understand the equation itself. But ultimately, a Q value comes out of what we said before. And that is, when you look at these elements, conservation of mass is shown here on the screen. But one thing that is not necessarily shown is conservation of energy. So what we have to do, well, actually, sort of both. What we have to do is we have to measure the total masses of both sides. To get the masses of this, you will have a chart that is in your textbook, specifically of isotopes /online. I think I have it. Where did I put it? I know it's some. I know I'll give you access to it, but you'll essentially have this page of this. This is not hydrogen. This is deuterium. Yeah, it's deuterium. Yeah, deuterium does not have the same mass as hydrogen, and sadly, you can't just take hydrogen's mass and multiply by 2 because there's a bunch of decimals involved. And by the way, you're going to need to use all of the decimals involved. I apologize, this is not a round to 3 decimal situation. So deuterium's mass is this right here, 2.14012. Nitrogen 14 is specifically this right here, which again, if you look up at nitrogen by itself, that is not that number, which is why you're going to have to pull it off of a table. So we find that the total mass of the left side is 16.17176 U. And if you get the right side, what you'll find is that it's very slightly smaller. So the mass has decreased. Since the mass has decreased, what must be the case here? No. Energy has what? Energy has come out of the reaction, and this reaction is exothermic.
Fire.
What's that? What did you say, liar?
No.
You said fire.
Fire. Okay, sweet. All right. So the easy way then to make that calculation is actually to do masses, find the difference of said masses, okay, in U, and then we talked earlier this chapter that 1 U was at a very specific amount of energy when multiplied by C squared, so you can use that to then calculate this amount of energy. What is this amount of energy right here?
The hydrogen bottom layer
the amount of
No.
the mass? That
This is how
coming
much
out?
energy is specifically coming out of this particular reaction right here. Okay? Now, the opposite can also be true. Oh, by the way, if kinetic, they'll do this for you in this case. If deuterium comes in, say, instead of just sitting right next to each other, if deuterium comes in with, say, five kinetic mega EV of kinetic energy, all they're showing right here is that, okay, the deuterium come in with 5 mega EV, add how much energy you just got out of the reaction, and Q is how much reaction, Q is the amount of energy coming out of the process. And this is quite simply just the original 5 plus however much energy you went in that particular case. Now, looking at the opposite, I believe, no, it's not the opposite, it's slightly different. Okay, we have helium and nitrogen 14 instead of hydrogen and nitrogen 14. And once again, we add them all up. We add all the mass on the left side, we add all the mass on the right side. And in this particular case, we find that the right side is heavier. It's more massive. So is that possible? Yeah, 100% it's possible, but this would be considered an endothermic reaction in this particular case. Once again, you would find the difference. The difference in this particular case is negative 1.194. So what would have to be the case in order to pull off this reaction? Something, like we talked about just a minute ago, has to come in with the kinetic energy greater than the kinetic energy of greater than the kinetic energy of 1.194. So it would have to come in with like 2 mega EV, and the difference, of course, would be how much you get on the very end. This calculates the minimum kinetic energy that would be necessary in this particular case. This is the, where's what? You know what, I don't think we're going to use that equation, so I'm not going to worry about it. So if the Q value is endothermic negative 2.17, then the minimum kinetic energy needed to react the nucleus must be, based on the fact that actually I kind of told you misleadingly, there's the kinetic minimum right here. So there's the absolute value of this right here. That's a 1. So what must be true of the kinetic energy coming in? Is it equal to 1.194, greater or less than 1.194? Must be greater, yeah. Must be greater than 2.17 in the case. All right, this enters in that we're done with this particular chapter. This has the stuff of the kind of biological part if you're interested in any amount of cancer research and stuff that they talk about as far as radiation and how they use that in there. That's at the end of the book. We're not going to talk about it specifically here, but from 1 to 11. Questions, concerns? How's the homework coming?
30%.
Cool. All right. We will probably finish chapter 30 tomorrow. And I fly through chapter 30 pretty quick because there's a lot of sections that I'm going to skip around and not worry about. I'm going to pick and choose a handful of those. And then we will probably look at stuff on Wednesday. Questions on homework on Monday, test Tuesday is the plan.
Dang it.
Are both of